Hey everybody, and welcome to our next video and our first unit, which is going to be all about density. You might notice I'm in a slightly different location here. I am in fact in my chemistry lab in my house, which is my kitchen. So you get a nice little sneak peek of all my little things. But anyway, we did that introduction lab where we were talking about density, and we started to see what makes something more dense versus not as dense. And we experience this density application just by looking at when we put ice water on the table at a restaurant. You put ice water out and you'll notice that that ice floats to the top. There's a reason why that ice floats to the top, and it has to deal with the density of ice versus liquid water. Before we talk more about that, let's actually formally define what density is. So density, which you've started to experience in that lab we did, is the measure of how much mass is in a certain space. So with that introduction activity, you measured 100 milliliters of each of those four liquids. So all four of those liquids took up the same amount of space. However, you were asked to find the one that was the heaviest of the four and put that in first. Because that had the most mass, given the amount of space it took up, that particular liquid had the highest density. And that's how we can determine how dense something is by looking at how much mass it contains per its given amount of space. Usually we say that's the mass per unit volume. So if I look at these two images here, both of these have equal volumes, and I can tell because both of these cubes take up the same amount of space, because that's what volume is. It's how much space something takes up. So they have equal volumes. However, this one on the left has less mass that occupies that space, whereas the one on the right would have more mass that occupies that space. So let me move my picture here so we could see those a little bit better. I'll move it in this corner. So because that one on the left has less mass given the amount of space, we say that that particular object would be less dense, whereas the one on the right would be more dense. And that's because it's heavier given how much space it takes up. It has more mass per unit volume. It is more dense. So we can experience density as well by looking at Italian salad dressing. So typically Italian salad dressing will have some sort of oil and it will have vinegar. And a lot of times they will separate, unless you're a good chef, which there is a way to prevent the oil and the vinegar from separating. You have to add one of two ingredients. You have to add either honey or you have to add Dijon mustard, and that prevents them from separating. That has to do with some chemistry that we're not getting into in this video, but if you don't put one of those in, we see that this very nice separation based on the density of those two liquids. But anyway, this top substance here has 0.916 grams per 1 milliliter. And that 1 milliliter is how much space it's taking up. So think about if you measure 1 milliliter in a graduated cylinder, that's how much space it's taking up. That oil would have a mass of 0.916 grams per that 1 milliliter. The vinegar on the bottom, however, has a density of about 1.05 grams per 1 milliliter. So per that amount of volume, per 1 milliliter, the oil has less mass given that amount of space, whereas the vinegar has more mass given the amount of space. So if we consider those particle diagrams again, the oil would have less stuff crammed into that amount of space, that 1 milliliter volume, whereas the vinegar would have more stuff crammed in. So because there's more stuff crammed in that given amount of space, that vinegar tends to sink to the bottom, and that's because it is more dense. So we'll see that the oil is less dense and the vinegar is more dense. Usually your oils are always less dense. That's why if you make soup, you'll see that you always have that oil rise to the top, and that's because that oil is less dense. It takes up less space per unit volume. So again, why does that ice float on top of water? And water is one of, or is the only substance that this happens to. When you think of a solid, a lot of times we consider, all right, solids are very compact. Their particles are very close together. Water is the only substance that when it is a solid, its particles actually spread out a little bit. So it becomes less dense, which is interesting. Water is the only substance that we know of that when it becomes a solid, becomes less dense. Normally we think of things, if they become a solid, they'll be more dense, so they'll sink. Water, this doesn't happen to. For reasons why we'll talk about in our water unit, actually. So those ice cubes are less dense. So again, if you consider that particle diagram, there's less stuff given that amount of space, whereas the water would be considered more dense. And we did something like this in class where we made that little density column, and we can compare densities just by looking at something like this. So our more dense materials are going to be down here. So these are more dense. So this is your steel screw, your honey, maple syrup, marbles. If we were to try to draw with the particle diagram what this would look like. So here's our honey. I'm going to try to draw a square that's about this size. I would have a lot of stuff crammed into that particular space. It is more dense. However, as I go up towards the top here, I'm going to try to draw the same size square. Now, I'm no artist, so please don't judge me. We're going to pretend they're the same exact size. But any of your oils are not very dense. So your rubbing alcohols, your water actually compared to a lot of other substances in the kitchen, not very dense. These guys would only have some particles given the amount of space. So this has less mass given the space. Ping pong ball floats on the top. Why? That's because it's really got nothing that comprises it. So its mass per unit volume is even smaller than that. So we can use, and let me just label this up here as less dense. We can compare, that does not look like a D, but it's okay. We can compare densities by looking at how they'll float on top of each other. Now we have to do this carefully because of course if we mix them too fast, they'll all come together and you're not going to see the separation, which is why when you did this in class, I had you pour them in very slowly so it was nice to see that separation. Here's another example of density, right? You buy raviolis from the store. Now, I don't make my own raviolis. I tried to once, and it was a disaster. I'll tell you that story in class because I'll never make my own raviolis again. But you get them from the store, and they're frozen. This happens with gnocchi as well. All of those raviolis will sink to the bottom, and the package tells you that the raviolis are done when they start to float. Now, why does this happen? That's because those raviolis have either ice inside of it or they have liquid water, so they sink to the bottom. Once those raviolis get nice and warm, however, you're forming gas particles that water is going to evaporate inside. And gases have very little mass considering how much space they take up. So gases are even less dense, much less dense actually. And therefore the raviolis will float to the top, and that's when you know they're done. So another application of density in the kitchen deals with making raviolis. So these are more dense, the ones that are not cooked yet, and they are less dense when they float to the top. And we can calculate density. Now we're not going to do too much of this in class, but I want you to see this equation. So if density is the amount of mass given how much space it takes up, your mass tends to be in units of grams right here. So we could use a scale to measure this. And the volume we can do just by using a graduated cylinder. So when you measured, for example, the 100 milliliters of liquid, that's how much volume that it took up. And the heavier the mass was, given an amount of volume, the higher the density. So we can calculate density by dividing the mass divided by its volume. And units for density, therefore, are going to be grams per milliliter, which we see there on the left-hand side of the screen. However, we're not going to use this algebraically. I like to use this triangle because I think this triangle is so convenient. It allows for you to solve for any variable in this density equation without having to manipulate math and reminding you of algebra. Because I know a lot of us don't really like math, so I try to make this as easy for us as we can. I always remember the order that this goes in. because you're probably at this point getting ready or have already gone to the DMV. So you'll see on this bottom corner right here, we have our density. So D, we have our mass up at the top, and then we have our volume. So I know it goes bottom, top, bottom, but it does spell DMV going across. And that's how we can manipulate this. Let's go ahead and see how to solve each variable in that density equation just using that triangle. So if I want to solve for the density right here, so notice to find density, they put density in bold. If I cross that out in this triangle, we see that density is equal to the mass over its volume, which if it's over it, it's going to be division. So if we're finding density, density is equal to the mass divided by the volume. Let's say you're given a problem where you're asked to find the mass. In this case, we could cross m out of the equation or in the triangle, and we could see that d times v is next to one another. D and v are next to each other. That means that in order to find the mass of that particular sample, I would take the density times the volume. So notice how this does not make you do all that algebra to solve. It kind of gives you the equation just by crossing off one of those variables that you don't need. So notice here, top and bottom, mass divided by volume. Mass is equal to density times volume. Now here, if I'm trying to solve for the volume, I cross volume out. Volume is equal to mass over, which is divided by, would be mass divided by its density, which if I move my picture here, we could see that the volume is equal to the mass divided by the density. So no matter how you need to solve a problem, this triangle gives you all three variations of that equation, which I really like. So if you draw the triangle, you do D and V, and you remember this little trick, you'll be able to solve for any type of density problem. Let's do two density examples together. So the first one is, let me move my picture one more time. Here we go. It says a cherry tomato is found to have a mass of 2.23 grams and occupies a volume of 2.17 milliliters. What is the density of the cherry tomato? What I like to do when I'm solving problems is I like to list all of the variables that I'm given, and I like to try to figure out what it is I'm trying to find. I think it organizes the information very nicely. So it says a cherry tomato is found to have a mass of 2.23 grams. So mass is equal to 2.23 grams. And it occupies a volume of 2.17 milliliters. So its volume is 2.17 milliliters. We want to know what is the density of this cherry tomato. So if we go back and we look at those equations, how do I solve for density? It looks like density is equal to the mass divided by the volume. So that's all I'm going to do to solve for this equation. I'm going to rewrite the equation just so we see which one we're using. And the mass is 2.23. Take your time when you do these. Don't try to rush, because if you rush, it's very common for you to switch those values by accident. Mass always has units of grams, and my volume always has units of milliliters. And if I solve for this on the calculator, we get a lot of significant figures. We get 1.02764,977. That's going to make me very anxious if you write that down. That has way too many significant figures, considering these measurements that were taken for that cherry tomato. We are dividing here. So this 2.23 has 3 significant figures, and this 2.17 also has 3 significant figures. So I want to round my answer so it also has 3 significant figures. My answer would be 1.03. We have to remember units as well. So in this case, I'm doing grams divided by milliliters. My unit would be grams divided by milliliters as well. And there is my answer to solve this problem. I wrote a lot of work for this. You do not have to write this much work every time. I'm just trying to show you the general idea of how to do this as we progress through these density problems. Let's try one more for good measure. A recipe calls for 125 milliliters of vegetable oil. So I'm going to list all of my variables that I have here. That 125 milliliters is its volume. How do we know? Well, one way to tell is because of the units, right? We typically use a graduated cylinder to measure volume. In the chemistry lab, that's going to be our milliliters. If the density of vegetable oil, so I have the density is 0.93 grams per milliliter, we want to know what is the mass of the oil. Again, you don't have to use that density equation. Let's go back and look at these triangles. So in this case, I'm trying to find the mass. So if I look at this middle triangle right here, the mass is equal to the density times the volume. So that's what I'm going to use in order to solve for this particular scenario. So mass is equal to density times volume. Mass is equal to density times volume. So let's go ahead and plug our variables in and solve. The density is 0.93 grams per milliliter. And I'm going to multiply that by 125 milliliters. And when you do that, you get 116.25. This also has too many significant figures, so we want to round it. This density value contains 2 significant figures, whereas this volume has 3 significant figures. We want our answer to have the lesser number of significant figures, which is 2. So how would I round this value to have 2 significant figures? We are going to round it up to 120. Now, if we're solving for the mass, you can remember, okay, if I find the mass of something, the mass is always in units of grams. So my unit for this would be the gram. If you're good at math, which some of you are, I'm sure, you could see that you would have units of grams, because if I have milliliters in one side and I have milliliters in the denominator of my density unit, those units of milliliters cancel out and I'm left with just units of grams, which we could see is the unit that's down there. We are going to do some density practice in class. I have a great soda lab that we're going to do where you'll investigate how you can tell if a soda is diet or regular just based on its density. And it's actually pretty cool. We'll do some work with that. If you have any questions, please don't hesitate to ask me in class, but otherwise I will see you in the last video for this kitchen math unit, and that is on accuracy and precision. So I will see you then. Bye.